I'll be presenting Think Before You Simulate: Symbolic Reasoning to Orchestrate Neural Computation for Counterfactual Question Answering. This work is done with some colleagues at Arizona State University and Samsung Research. Visual reasoning about physical dynamics is a difficult problem and requires an understanding of the underlying causal structure of the scene. However, prevalent neuro-symbolic models haven't taken full advantage of the neuro-symbolic approach. These models often lack explicit reasoning about the scene and blindly simulate from the beginning of some counterfactual scenario. Consider CLEVRER, a challenging benchmark which is about physical dynamics and tests multiple types of questions, such as descriptive, explanatory, predictive, and counterfactual. Descriptive and explanatory are easier since they just ask to reason about some video. Predictive is harder, requiring simulation. We focus mostly on the hardest type, counterfactual reasoning, because neural networks typically aren't good at reasoning, and explicit causal reasoning could help here. There are some available models that already tackle this problem. NSDR is the baseline that was presented along with the CLEVRER dataset. It's a neuro-symbolic model that uses symbolic reasoning integrated with language, vision, and dynamics. DCL and VRDP use a similar approach, but incorporate concept learning and differentiable physics, respectively. ALLO is an end-to-end model which is based on attention. These outperform the baseline NSDR. What we're interested in is improving NSDR and similar models by augmenting them with explicit reasoning using answer set programming. Our work can be built on top of these models. We apply our technique to NSDR and VRDP. Doing so makes our work the best performer. Answer set programming is a declarative logic programming paradigm, which is well known in the symbolic AI community. It's useful for knowledge-intensive tasks and combinatorial search problems, and it has its roots in logic programming, knowledge representation, constraint solving, and deductive databases. Here is an example of the Hamiltonian cycle problem, represented in ASP. In xy represents that the edge xy is in the Hamiltonian cycle. The first two rules specify that for every vertex, there's exactly one incoming edge and one outgoing edge. Next, we designate some node 1 and say, if the edge 1x is in the Hamiltonian cycle, then it's reachable. Further, we make reachable a transitive closure. And this is the reachability condition. Lastly, we say that every vertex must be reachable. If you give this program to answer the solver, it will find the Hamiltonian cycle. Baseline NSDR, along with VRDP, takes in a text query and video, and is composed of a question parser, which is in the form of an LSTM encoder, a video frame parser, which is a masked RCNN, a dynamics predictor, and a program executor. The program executor is a Python implementation of functional modules. The simulator is a propagation network in NSDR, and in VRDP this is replaced with a more accurate differentiable physics engine. As a motivating example, consider the trajectory on the left of some scene in the dataset, along with the two queries below. Without the blue object, will the cyan object and the purple object collide? And without the blue object, will the green object collide with the orange object? The ground truth says that both of these collisions will happen in a counterfactual scenario. If we do pure simulation, errors tend to accumulate, and after 100 frames in this example, it's predicted that no collision happens. However, notice that simulation isn't necessary for all but one object in the scene, the green object. This is because the green object collides with the object to be removed and is therefore affected. Furthermore, the simulation of the green object isn't required up until this point. We will end up using this insight to improve upon the baseline models. So what we did was use the same basic framework that NSDR and VRDP uses, but instead, do not necessarily simulate from the beginning of the scene. We use CRCG to determine the presence of causal relationships in the original scene between removed objects and the rest of the objects. This information is integrated into an enhanced simulation, where only objects that need to be simulated are. Concretely, the simulation starts by initializing all objects as non-simulated. That is, we can use the perception result in the scene instead of simulating. If an object interacts with the object to be removed in the original scene, then that object must be simulated from that point on. Furthermore, if an object interacts with a simulated object, then that object needs to be simulated as well. Overall, this process saves a lot of simulation from happening, and hence provides higher accuracy, since perception is much easier than simulation. And if we don't have access to a frame-by-frame simulator, explicit reasoning can still help. Take the case here, where we imagine the blue cube removed and ask if the green cylinder and the cyan object collide, and if the cyan object and the purple sphere collide. We can reason that the blue cube does not affect the initial collision between the cyan object and the green cylinder, so this should still happen. The collision between the cyan object and the purple sphere is a little trickier, but since the blue cube does not affect the cyan object or purple sphere before they collide, then CRCG's approximation assumes that this collision will still happen. Here is an example of the causal graph of the previous video, but with the brown object removed, since it does not affect anything. Each node is by default an ancestor of itself for each collision that happens. This is denoted by the vertical arrows and is represented in the first ASP rule. The horizontal connections are created when an object collides with another, making them mutual ancestors from that point on. Finally, the ancestor relation is transitive. In this example, the blue object is removed, and the states affected in the original scene are outlined in red. These nodes outlined in red now share the blue object as a common ancestor. The purple and cyan objects collide at frame 100 and are determined to not be affected by the blue via the ancestor relation. Therefore, the collision can still be predicted to happen in the counterfactual. We additionally applies CRCG's approximation to the CRAFT dataset. And instead of using the video to be parsed, we use the provided description. In this instance, the question asks if the small red circle will end up in the basket if the small green circle is removed. CRCG's approximation determines that the green circle is not relevant and the problem can be answered without simulation, for this example. Furthermore, we can rephrase the question as a perception question and ask GPT to answer it for a similar improvement. Instead of, will something happen if this object is removed, we ask something like, did something happen in the video? Here we show the results. We improve both NSDR and VRDP substantially with our enhancement. Though VRDP has a much better simulator, it still accumulates errors in simulation, while we simulate only what is necessary to improve performance. In conclusion, we improve neuro-symbolic architectures by using an enhanced simulation which incorporates reasoning about perception. Furthermore, we can still use reasoning when a frame-by-frame simulator is no longer available. Our enhancements are orthogonal to the baselines, which retains the modularity of the overall architecture. And though an end-to-end attention-based model can perform fairly well, as longer time horizons with more objects and more physical events are included, they may not. And enhancements via symbolic reasoning may be needed. Thank you.